Hi. In this first presentation of the second part of our course, we will start looking into finite state machines with data path, or FSMDs as they are normally called. After watching this presentation, I hope that you will be able to explain what's an FSMD and also what this type of circuits are used for. Also, to differentiate between the behavioral representation mechanisms that are used for finite state machines and for finite state machines with data path. And finally, to identify the main building blocks of a finite state machine with data path. So FSMDs are used to specify and implement systems that are described at an upper level that we normally call register transfer level, where we work not only with single bits but also with multi-bit registers, such as adding or multiplying the values stored in two 8-bit registers, for example. The architecture of such systems includes a controller and a data path. The controller is normally a finite state machine and generates the commands for the various blocks that are present in the data path, which in turn comprises registers to store data, combinational blocks to perform operations over that data, routing networks to transfer data among registers, and even after other finite state machines to perform various sequential operations. So this slide shows an example of a register transfer level operation. In this case, we have two registers, A and B. They could be 8-bit registers, for example, and two combinational blocks, one to subtract the content of the two registers and the other one to increment the result of this subtraction. And of course there are the routing networks to take data from the registers into the combinational blocks and the result into the destination register A. We are assuming in this example, as you can see in the waveforms below, that register A stores the value 9 in the beginning and B stores the value 3 throughout all this period. Now, the subtraction of A minus B will generate 6, and adding 1 will generate the final result of 7 after the first clock cycle, which will be stored in register A. Notice that the value stored in A is generated by the two combinational blocks, so it will become available shortly after the rising edge of each clock cycle, since we only have to take into account the propagation delay of the combinational blocks. So the operation A minus B plus 1 is repeated for every rising edge of the clock, updating the value of A while B remains unchanged. Now, this example shows a slightly more elaborate case, including the operations associated with an ASMD block. In this case, you see that all the ASMD block components deal with register transfer level operations. The state box decrements the content of register R1. The decision box compares two operands A and B, and the two conditional output boxes update the content of register R2 according to the result of the operation performed in the decision box. You should take a moment to relate the ASMD block shown here and the block diagram shown on the right, where we find a structural representation of the various operations. and that are associated with state S0. By looking at this diagram, you will notice that all combinational operations are performed in parallel, that is to say, at the same time, but the destination registers will be updated with the corresponding results only when we are in state S0, according to the state register control signals at the bottom. You should keep in mind that the destination registers are updated only at the moment when the FSMD exits the ASMD block, that is to say, at the next rising edge of the clock. You may pause the video at this point if you want to go through the various boxes and blocks and on the left and on the right, and to notice how they interact to implement the various operations that are represented here. Notice also that all these boxes and blocks represent elements that belong to the FSMD data path, not the control path. But the control path will, of course, generate the state register signals to identify which registers are to be updated. So, according to what has been said so far, the architecture of an FSMD can be represented as shown in this slide, where you see the control path and the data path above. Notice that the control path comprises a finite state machine containing the usual state register and the combinational logic segment needed to generate the next state information and the million Moore outputs. On the other hand, the data path contains the combinational blocks and or finite state machines needed to implement the required functional units, and the routing networks needed to transport data from the source to the destination registers, and also, of course, the data registers themselves. It is important to notice also that the flow of information between the two paths, with status signals being transferred from the data path to the control path, and control signals being fed back from the control path to the data path. These control signals are, of course, needed to identify which operations are required to take place at any given moment, and likewise to how to store the results. So apart from these internal signals, there are, of course, the external data inputs and outputs, and the external command inputs to the control path, and external status outputs. You should keep this diagram in your mind and go through the exercise of relating it to the actual circuits and signals that will be used in our exercises throughout the rest of this course. For each specific example, try to map each block to the corresponding block shown here, and likewise the internal and external signals. Thank you for your attention.